We shall discuss the next problem based on helical torsion spring. So design a helical torsion spring for a window shade made from patented and cold drawn steel wire of grade 4. Here they are asking us to design the spring and they have given the material of the spring. The material is patented and cold drawn steel wire of grade 4. The yield strength of the material is 60% of the ultimate tensile strength and the factor of safety given is 2. So they have given the yield strength of the material is 60%. We shall write this. Yield strength is 60% is 0.6 of ultimate. Sigma y is equal to 0.6 sigma u. The factor of safety given is 2. We shall write the factor of safety. Due to space consideration, the mean diameter is kept at 18 mm. The mean diameter capital D is maintained at 18 mm. The maximum bending moment acting on the spring is 250 Newton mm. So the bending moment, we shall take this as torque. We shall consider this as torque. The maximum bending moment is 250 Newton mm. The stiffness of the spring should be 3 Newton mm per radian. Stiffness is F naught. Stiffness of the spring F naught is equal to 3 Newton mm per radians. So they have given this much amount of data. They have given material of the spring. So we shall refer data handbook and we'll take material. So in page number 195, they are given table 11.7 physical properties of patented and cold drawn steel wire unalloyed. So in question also they are given the same material. They have given in question grade 4. So here they are given grade 1, grade 2, grade 3, grade 4. So in brackets they are given 1, 2, that we should not consider the term present inside the bracket. We have to consider here grade 1, grade 2, grade 3, grade 4. So here grade 4 they have given. So out of this grade 4 we can select any material. Here they have given wire diameter, uncoated wire diameter. So here they have given. So we shall consider 1.5. The wire diameter as 1.5 and corresponding the tensile strength is 2260. Here they have given wire diameter and they have given tensile strength in Newton per mm square. So we shall consider that value, and also at the end of the table they have given modulus of elasticity E and modulus of rigidity. We shall consider these values from table 11.7, page number 196. I'll consider the diameter of wire as 1.5 mm and the tensile strength is sigma. We shall consider corresponding to 1.5, the tensile strength is 2260 Newton per mm square. Modulus of elasticity and modulus of rigidity they are given. We shall take it 210790 Newton per mm square. And modulus of rigidity they have given as 88370 Newton per mm square. Now using this data we shall find one value. The allowable stress is given by yield stress by factor of safety N. The allowable stress or induced stresses is equal to yield stress by factor of safety. But yield stress in question they are given 0.6 times ultimate, so we'll consider 0.6 sigma ultimate by n. So the ultimate stress which we have considered from data handbook is 2260 by n. The n factor of safety in question they are given as 2. So if we solve this, we'll get the stresses as 678 MPa. Now we'll find the spring index C. D is 18 mm, they have given in question, and by 1.5. So the value of C we will get as 12. So from data handbook we shall find the value of stress concentration factor. For torsion springs, we'll consider the maximum stress equation and the stress concentration factor equation. The value of K we'll get by solving this equation is 1.066. Now we'll find the maximum stresses induced in the spring wire. We'll take the equation 11.25a. We'll take this equation. On solving this equation, I'll get the maximum stress induced in the coil is 820 MPa. This the induced stresses is 820 MPa. This is more than the stresses which we have considered 2260. So this is more than the working stress. Here working stress we have found out as 678 MPa. So this is greater than 678 MPa. So the design is not safe. We need to consider the spring wire again from the data handbook, because the induced stress is 820 MPa and the maximum allowable stresses in the spring material as per the design is 678 MPa. So this value is exceeding 678. So we cannot go further with this value. We have to change the value from the data handbook. From data handbook we had considered the diameter of spring as 1.5 mm. We had considered 1.5, and for that corresponding value we had considered 2260 grade 4. Now we shall go little further, higher value. We shall consider some higher value. We will take 1.7 mm dia, 1.7 mm dia, and the corresponding tensile stress is 3220 MPa. So again from data handbook, the diameter considered is 1.7 mm, and the stress induced is 2220 Newton per mm square. The modulus of elasticity and modulus of rigidity remains the same. So now for this value we shall check. We shall consider this as sigma t. This as sigma t. Sigma t is equal to 0.6 times ultimate stress by 2. For ultimate stress we shall consider this value 3220. So the value of sigma t we will get is 666 MPa. We shall again find the value of spring index C. We will get the value as 10.6. So we will again find the value of stress concentration factor. The value of stress concentration factor which I will get from this is 1.076. We will find the stresses induced in the material. We are considering the same equation. In this equation I am substituting the value of D and K. D and K. The stress which I am getting now is 569.7 MPa. So this value is less than the value which I have found out here. So the maximum stress is 666 MPa and the value induced stress in the spring material is 569. So the design which we have considered is safe because the induced stress is 569 and it is less than the maximum stresses allowable in the material 666 MPa. So the diameter which we have considered as 1.7 is correct. So now we can proceed further with this diameter. Now Now the diameter is 1.7 mm. From data handbook we shall consider the formula for stiffness. Stiffness y is equal to TLD by 2EI. And the value of stiffness is equal to F naught is equal to T by theta. This equation, the equation for stiffness F naught is equal to T by theta, it is not available in data handbook. So you need to remember this equation. First we'll find the number of turns now by using this equation. Theta is equal to y by r, F naught is equal to T by theta, and y is equal to TLD by 2EI. So this is the formula. Now what we shall do is we shall substitute this equation in y. We shall substitute this equation in y, and for theta we shall substitute this theta in this value. So we'll get the F naught in terms of this values we'll get. I am substituting. So for value of y I am substituting in this equation now. TLD by 2EI divided by r. Now I will substitute this equation, theta is equal to this equation, in F naught is equal to T by theta. Here I will substitute. On simplifying this equation, I will get F naught is equal to because the value of I here, this I is moment of inertia, pi d power 4 by 64, and the value of L, this L is pi I d, pi I is number of turns and d is the diameter. So on substituting and simplifying, I'll get F naught is equal to E d power 4 by 64 d into I. Now I can easily find the value of number of turns I, because I have all the other values. In question they have given F naught as 3 Newton mm per radians, and E we have taken from data handbook. So the number of turns I can find out is 509.4 turns. So we shall approximate this to 510 turns. 510 turns. Now we shall find the deflection y. we'll consider this equation y is equal to TLD by 2EI, and we'll find the value of deflection. L is pi ID. So the deflection y I'll get by solving this equation is 750.86 mm. And finally we'll find the length of coil. So length of coil is pi ID. Two double eight three nine point 82 mm. So the total length of the spring is 28839.82 mm. So we have designed the helical torsion spring. In next class we shall see new type of spring called bevel springs.